Well, here we are with the third part of lecture one, and I'm going to pick up the pace because normally it takes me a 2 hour lecture to go through one of these chapters, and I'm finding I'm going way too slow because I'm doing it in segments. So I just want to make key points, and we'll try to get this done so it doesn't take forever. One of the things that's important to realize is the pioneers of quantum mechanics, those people who were prominent scientists in the very early 20th century, were all trained in the classical physics of Isaac Newton and the theory of electricity and magnetism created by Maxwell in the 1860s. And they also were trained in thermal physics. That is the description of how heat influences gases, solid bodies, and so forth. And they all were steeped in this and were highly influenced by the properties of thermodynamics. Here's some historical events in the development of thermodynamics, starting in the early 1800s and continuing on to the point where quantum mechanics started in the year 1900. All of these people, and that includes Max Planck, Einstein, Niels Bohr, these were the fathers of quantum theory. And in addition, Kirchhoff, a German, developed a number of descriptive laws that define how heat behaves by observation and experiments. He was quite a good experimenter. And in fact, it's noted here, he discovered two of the elements that had been previously missing in the periodic table. And Kirchhoff's laws also pertain to something called black body radiation. This is the heat radiation you can feel if you stand near a fireplace or a stove. And in the 1870s, when Kirchhoff was at his prime, there was no underlying description of the laws he had found. So he had found laws that were reliable but unexplained. And so there's a discussion here about these things. And there were other observations that had been made. For example, using microscopes, people could see motion of little pieces of dust or debris on a slide in a microscope with no apparent explanation for why these little objects are moving like this. So this is another example where I've clicked on one of these green boxes and it throws you into this animation of the random motion of small particles suspended in water. A pioneer in understanding this was Reverend Brown, and it became known as Brownian motion. So there were little hints that there was more to be learned about the physical world in terms of Kirchhoff's laws of thermodynamics, which were, as I say, they were reliable but unexplained. And indeed, the mood by the end of the 19th century was that we understand everything about the universe. You can find quotes from famous people about this, that we know everything. We have a few loose ends. We can't explain, this is what they said at the time, we cannot explain an equation that depicts the radiation from warm bodies. We can't explain Brownian motion, and so forth. In addition, there was doubt about the reality of atoms. There was debate about whether the Greeks were right, that atoms are indivisible little objects. But in the very late 19th century, the structure of the atom began to reveal itself. The electron was discovered, various other features of the subatomic world began to appear, and there's a discussion here about those things. By the way, here's a modern picture of the black body curve that people were confounded by back in the 1800s. This is a picture of the heat radiation of the universe left over from the Big Bang. This is a black body curve that was obtained in a spacecraft mission in 1990. This created a revolution in our understanding of cosmology, but I wanted to show you that this is the shape of the black body curve that was unexplained until Max Planck explained it in 1900. I've already talked about electricity and magnetism. These were very well-developed ideas from Maxwell. And in fact, applications were underway in the late 19th century. The first efforts to produce radio and so forth, the telegraph, the light bulb, all these things were becoming available. Another mysterious thing in the late 19th century was the chemists could isolate various kinds of elements, gaseous elements in this case, and put them in a tube and connect electrically here and here and run an electric current through the tube, and you'd see what's called a glow discharge or words like that. And technology had advanced to the point where people were able to isolate the different colors in this emission from this, in this case, it's hydrogen in the glass tube. And what they saw was this. They saw some blue lines and a kind of a bluish green or an orange and so forth. So again, we had observation without understanding. And it took just a few more years before the real beginning of quantum mechanics to explain why these isolated colors were present in hydrogen. Incidentally, you can buy your grandchild, if they're interested in physics, you can buy them one of these shirts. There are lots of different varieties of this. These are Maxwell's equations describing electromagnetism. And if you go to the physics building at any university, you'll see this shirt or something like it everywhere. Here's the blackbody spectrum of the sun, this yellow, and it's not quite an ideal blackbody because it's influenced by the components of the corona, the shell of hot gas, the corona around the sun itself. That has an influence, but you can see it matches this ideal blackbody curve, this gray curve, and this gray curve has a temperature of just about 6,000 Kelvin above absolute zero. So we see the sun is pretty much like a black body, but spectroscopy, those individual color lines coming out of that discharge tube I showed, led to eventually to understanding, first primitive understanding of atoms in the first 10 years of the 20th century, that for something like hydrogen, passing an electric current through the hydrogen increased the energy of some of the electrons so that they are in a higher energy level that falls to lower energy levels, and in that process they release light. And this reignited the debate about, is light waves or particles? Maxwell's equations show very clearly that light and its associated other parts of the spectrum like radio waves, X-rays, gamma rays, they're all part of the same spectrum and they behave like waves. But when we look at the properties of the hydrogen atom, which has a single proton and one electron, we find that it's more likely to be coming from individual events where the electron energy changes from one level to another, all described by integers. So we're beginning to talk in a quantized kind of way about how nature behaves at the atomic level. that these transitions were observed in the spectra that I showed right here, these individual colors. So the first hints on how to think about atomic structure were going on in the early 20th century, but still the concept introduced by Newton of corpuscles, of of light as little chunks of energy, that was still considered to be in doubt. And Einstein turned out to be the big advocate for changing that thinking and allowing two versions of light to be pertinent. One was Maxwell's wave equations, and the other was a new interpretation of Newton's corpuscles, namely little puffs of energy we now call photons. And so Einstein was instrumental, and it took more than a decade to convince the community that the spectral observations made of different elements in discharge tubes and other experiments prove that light was could be conveyed in the form of particles. So we have an even more focused issue of the wave-particle duality I talked about in the first part of this lecture. It also turned out that the lines of emission, the color emission from hydrogen, here's one of the hydrogen lines, there's another. Turns out that Balmer, who was a high school teacher but studied the spacing of these lines, discovered a simple equation to describe the properties of the emission from hydrogen. All you have to do is pick two integer numbers and put them in this simple equation, and you can define where all these lines are going to occur once you know this number. It's called the Rydberg constant. There it is. But that's not the important part. The important part is the knowledge, descriptive knowledge of nature in the case of emissions of light from energized gases was growing. So by 1900, there was a body of knowledge unexplained, and this equation later was derived by Niels Bohr in his first attempt to describe the behavior of the hydrogen atom. Here's yet another example of the transition of these transitions of energy levels in hydrogen. Some of these are visible. They're called the Balmer series. Some are not seen because they're in the infrared, beyond the scope of the human vision, and some are in the ultraviolet. So as instrumentation developed to be able to measure ultraviolet and infrared radiation, more knowledge was obtained about the structure of hydrogen, and gradually the concept of electrons in atoms became an accepted way of thinking about the atomic world. Relativity was also around. In 1905, Einstein produced his first theory of relativity, and roughly 10 years later, produced his more elegant version that explains the behavior of gravity. And this was a challenge to understand how to merge Einstein's relativity with the observed properties of the quantum world. And I always show this equation. This is one of Dirac's equations from the late 20s, describing the behavior of electrons. It's extremely elegant, has just a little bit of ink on the paper, kind of like Picasso's drawing of a nude. There's just not much ink there, but you get the idea. And this is the direction in which physics was going in the 1920s. Try to explain with compact mathematical tools what is going on in the subatomic world. So there's a discussion here of relativity. So we have these people. These are not the only pioneers or heroes in the early days of quantum mechanics, but it's Einstein, Planck, Kirchhoff from the 19th century and Balmer explaining the colors that come from hydrogen atom. At this time, all these people, if they had all these people had PhDs, and they were all of those degrees were awarded for their work in topics in classical physics like thermodynamics, astronomy, and related topics. Here's a little aside about me. This is the production of PhDs over the last 60 years, roughly. And one thing you don't want to do is come out of school when there's a glut of new graduates. And right there is when I got my PhD. There were no jobs. It was exciting times. Anyway, at this point, I do an optical demonstration. I'm not going to do it right now, but the idea is I purchased a kit. This is an enlargement of a piece of 35 millimeter film on which we see a single slit, a double slit, 3, 4 slits. And then if you could see this in up close, you'd see there are just hundreds and hundreds of alternating dark and light lines here and here. And in the classes I teach where I'm in the room with students, we use this piece of film and use a laser pointer and demonstrate Young's experiment by shining the light on this double slit. And this is what you see. This actually, I think, is the result from 4 slits. So unfortunately, hard to do that without having you in the room. So I've already mentioned, and I'm going to skim through this quickly, that the concept of the atom in the 1800s was an array of competing ideas about what is the structure of the atom. And we had this kind of early idea, this is called the plum pudding model, here from Thomson, that there was some kind of central object, or that the atom had a structure like this, where you had something like the batter in plum pudding with small negatively charged objects, electrons distributed throughout. But Rutherford, who was a genius experimenter, set up an experiment like this. There's larger drawings of this in other chapters. He had a radioactive source. And of course, radioactivity had emerged as an unexplained phenomenon in the late 19th century. Madame Curie and her colleagues were constantly working with radioactive materials like radium, and people were producing artificial radioactivity by creating X-ray tubes and so forth. So there was work in that regard. So what Rutherford did is he got a radioactive source and let the output of that radioactive material strike a gold foil. And the thinking was, if this model were correct, the beam of radioactive material would pass through and all the energy would be deposited here on the inside of a cylinder with essentially photographic material on it. But what Rutherford found was lots of the radioactivity exposed the film here, but occasionally you'd see a spot here, 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 here. And what's going on? And the answer was the emission from the radioactive source rarely, but occasionally, would actually strike a large, dense object. I shouldn't have said large. A very dense object in the center of the gold atom and cause that particle to scatter. And this became the model for the structure of atoms. That is, there's a dense nucleus surrounded by a charged particle, an electron in the case of hydrogen, or many electrons in the case of heavier elements. So here's a more detailed picture of the Rutherford experiment. So we have radium in here, a stream of particles coming out. And as I say, most of them struck here, but occasionally you get a particle here and here. Again, not explained. So Rutherford came up with his model that the gold atoms have a dense core, and we now know that dense core is incredibly tiny compared to the size of the atom. So, and here's a history. And this, you'll see this occasionally in the book, where I turned a big page sideways because there's too much information to show it on a standard page. And here's some more history. Here, sequence of events in the emerging idea about the structure of the atom. Here's a picture of Neil, or a sculpture of Niels Bohr. Is a picture I took when I was in Copenhagen a couple of years ago. And so what we have at the beginning of the 20th century is observations about the behavior of the quantum world, observations like these of what happens when you pass light through double slits. And here's the comparison of 2 slits, 3 slits, 4 slits, and so forth. And so we had a lot of observation without explanation. The interesting thing is that we now know that electrons can also go through a double slit experiment, and they behave like waves. If you set the experiment up properly, they behave like waves. Now, let me show you what this is about. Experiments have been done where you have a double slit experiment, but you only send one electron at a time, not light, but electrons. And you send one electron at a time through the experiment, and after maybe 15 minutes, you can see there's some little dots on a detector where the electrons have struck. If you wait an hour, you see this. If you wait 10 hours, you see this. And if you wait 40 hours, so I think it took about a week to do this, you see the behavior that looks like light going through a double slit. And remember, I want to emphasize again, when you see this kind of fringe pattern, that indicates wave propagation, not particles. So we have, in the case of a repeat of the Young experiment back in 1808, doing it in a modern laboratory with electrons, we end up seeing the fringes that Young saw, but we're using electrons, which we normally think about as being little objects like BBs or something. But it turns out if you design your experiment right, you can get them to behave like waves. And we're going to constantly be confronted by this comparison between particles and waves. And the interesting thing to me is each one of these dots was produced by a single electron. It was the only one that was in the experiment at any given time. And somehow the individual electrons know that they're not supposed to end up in these dark areas. So we'll be talking more about that as we progress. We've even got experiments using something called fullerenes. These are structures made of 60 or 70 carbon atoms, and with a little chemistry magic, you can create these things so they look kind of like a soccer ball. They're named after Buckminster Fuller, who back in the 40s and 50s invented a architectural scheme for building spheres that looks almost identical. So these are called fullerenes, and in the right experiment, you can get fullerenes to exhibit fringes, passing them through something like a double slit experiment. So here we're having wave-like behavior from a particle, still an atomic particle. It's still, you can't see the little fullerenes, but you can see the fact that they're behaving like waves because you don't get these fringes, these bumps, unless they behave in a wave-like manner. So we have a discussion here about what's different about the quantum and classical worlds. This is Richard Feynman, one of the pioneers of physics in the 20th century, a Nobel Prize winner. And this discussion you can read, it's non-technical, but it does discuss what's observed when we use sophisticated instrumentation to observe behavior of quantum particles. Now, I mentioned informally, I mentioned a wave function before. This is how we mathematically describe the behavior of quantum systems. We have an equation that tells us how the wave function behaves. As long as we know the environment in which the electron or photon is contained. And if you click on this, you see how wave functions change over time. This is a animation of a idealized, what's called a harmonic oscillator, like a pendulum. And you see these little functions changing shape and position. That's the way the wave function, and we use that symbol, PSI, I pronounce it psi, like when you SIGH. So we are introducing terminology that we'll be using over and over again. And we talk here about the energy levels. I've already explained the energy levels of hydrogen can be changed by passing an electric current through a hydrogen gas. And when that happens, the lowest energy state, which is shown here, changes to higher levels. And you see these very interesting patterns that occur. And the extraordinary thing about quantum mechanics is the mathematics of the wave function gives us these shapes. And these shapes tell us the properties of the light that should be emitted when the energy levels drop back down to the lowest level. And that's exactly what we observe. And they have these kind of odd little shapes shown here. So the mathematics we have is mature and shows us exactly how hydrogen and other atoms behave when we energize them. And there's a variety of different ways of doing that. Now we're coming to near the end of this chapter. And so I have this little discussion on the philosophy of science and the issue of reality. When we say we can describe quantum systems using the wave function, are we really describing nature's reality, or have we just invented a way to describe it with clever mathematical schemes? And that's this section discusses this topic. We know we can't, I'll just quote myself, we can't be far off. And here's why we know this. The calculations that are done since the late 40s on the properties of electrons, particularly their magnetic properties, produce this number for the magnetic property of the electron. When we go in the laboratory and measure this, which is an exquisite measurement, difficult to do, but look at the comparison. We get the same number. We don't see a difference till we get to I think the 10th decimal place. So we must be on the right track. But the underlying reason why our mathematics is able so successfully to describe the quantum world remains a mystery, and we will discuss this throughout the class. In addition, quantum mechanics was invented to describe atomic physics. That is, the light emitted by atoms, how atoms interact with one another to form molecules and chemical compounds. But it turns out the same theory, the same mathematics, gives us what we need to know about the nuclear physics of atoms. That is, that little nugget in the center, the nucleus, is made of pieces even smaller than proton or a neutron. We have the quarks. Here's the electron and its two heavier cousins, the muon and the tau, some mysterious particles called neutrinos, and a variety of other particles. Quantum mechanics also describes this world with an extremely successful model called the Standard Model of Elementary Particles. I call this the subatomic zoo. So we have all this success in describing atoms and the pieces of atoms, but there are mysteries. One of them is here, I'm going to defer talking about this until probably chapter 3, but you can read this at your leisure and see if it makes sense to you. So the real question is, why did I create this class? Well, I mean, what is the motivation to spend all this time? You're going to spend 12 hours with me talking about quantum mechanics. Why are we doing this? And the reason is that we have a theory in our hands that we know works. We've invented a huge variety of applications that all depend on understanding the quantum world. And that's great. I mentioned that earlier in the lecture on this chapter, that we have all the technologies related to medical devices and navigation and communication and computers and our modern world. But our success, and I quote myself again, our successes do not convince us that we truly understand the details. And there are many competing interpretations of the equations. Everybody agrees on the equations. There are many interpretations related to why quantum mechanics works. And this discussion introduces you to some of those issues. If you read this, you'll see why we have a microwave pictured there. And the principal issue is this. It's called the measurement problem. Using the mathematics that we have and a small number of laws or rules, we can predict how quantum systems evolve. They change over time and over space. And then we do an experiment on, let's say it's an electron. And the quantum theory we have predicts the probability of various outcomes for the experiment. Doesn't predict the exact outcome any more than we can predict when a radioactive atom is going to decompose. We just wait, and every once in a while, one of them decomposes. So the real issue is, why do we have a successful theory that very accurately predicts how quantum systems evolve in time and space? But once we do an experiment, we can't predict the outcome. This is called the measurement problem. And another way to say it is these two researchers have a, obviously very elaborate experiment in front of them. Somewhere in here, there are quantum particles that are being studied by this elaborate apparatus. But at what point does their quantumness make a transition to the macroscopic world of this laboratory with things as big as human beings and various components here on this laboratory bench? Where is the transition between the quantum world and the macroscopic world that we live in? There are many questions related to this, and they are all under the rubric of the measurement problem. There's some discussion here of Einstein's views of the problem with quotes. I leave it to you to read those. And there's a discussion here about why I chose to write this book. I could not find any book that did enough detail to satisfy me and wasn't too technical and would put off the normal non-specialist. So here are the takeaways for chapter 1. We have the emergence of science, mostly begun by doing experiment or observations of astronomy, that led people to realize, particularly Newton, that the universe is an observable place that can be described by laws and mathematics. And it started an enterprise to develop a physical science to understand the nature of the universe. And for hundreds of years after Newton, that enterprise was quite successful. The big surprise came in 1900 when quantum mechanics emerged. It's described here. And quantum mechanics has been put to use by society to make us the richest civilization that has ever existed on Earth. But that same science challenges us to come up with self-consistent descriptions of nature compatible with our intuition. And in many ways, quantum mechanics fails to behave in a way that our intuition would like to see. Cause and effect, we've already discussed that. That's an example of conflict between our intuition and the way the subatomic world works. So there's more here that you can read. And you'll be ready for the content I'm going to present in lecture 2. And there will be a video of that lecture as well. Here's a little cartoon to bring us to a close. The cartoons in the book were done by my cousin, Dave Meidrich. So this is one of the key equations in quantum mechanics. We don't have to get into any details about this. Just treat it like a piece of artwork. And here the professor is telling the student, it's Murphy's Law. So with that, I'll bring this to a close. Oh, there's some history. There's a piece of artwork here that captures the history of quantum mechanics over the centuries. And with that, I'll close, and then I'll see you next week for more.